If I asked you to name the top refactoring hotspots in your project, could you? I bet you could. But beyond the obvious ones, often some serious hotspots remain hidden, lurking in the dark. Let me show you how graph theory can become your new favorite screening tool to reveal these hidden complexity hotspots. And here's the best part. This approach has two key advantages over traditional tools like NDepend and SonarQube. Stick around to see why that matters. Let's start with a classic example of graph theory in action: cycle detection. While cycles at DLL and assembly level are usually prevented by build systems, cycles at the class level are perfectly possible in most programming languages. Circular class dependencies make the system harder to understand and maintain, especially when analyzing the impact of changes. Even worse, cycles can lead to non-deterministic behavior, particularly during system startup, where the order of initialization can become unpredictable. Next, let's talk about degree centrality, a simple yet powerful metric in graph theory. It counts the number of incoming, outgoing, and total edges per node. A class with a high in degree is heavily dependent upon. This means it's stable in the sense that changes to it will have far-reaching consequences. Carefully review these classes and decide whether this stability is intentional or a liability. A class with a high out degree has many dependencies. While this might be fine for the composition layer, in most other cases it likely violates the single responsibility principle. A class with a high total degree acts as a connectivity hub. I can't think of any valid reason for allowing such super-connected classes in a well-structured codebase. Now let's go one step further. Betweenness centrality is a slightly more advanced graph metric. It measures how often a node lies on the shortest path between other nodes. Classes that rank high in this metric often act as brokers between different clusters of functionality. They might be critical for component integration and feature collaboration. But they can also become hidden coupling points, tying together modules that are supposed to be independent. Any class that ranks high in betweenness centrality is worth checking. Is it truly meant to play that role? Just like betweenness centrality applies to nodes, edge betweenness applies to dependency between nodes. This metric identifies dependencies that lie on many shortest paths between classes. It highlights key dependencies, the ones you would need to break up if you want to make your design more modular. There are many more graph-based metrics for measuring modularity and cohesion, and I'll cover them in a future video. So don't forget to subscribe so you don't miss them. A graph metric that has been used in network analysis since the 1950s is closeness centrality. It measures how central a node is within a network based on the shortest paths to other nodes. This metric ignores edge direction and focuses on how interconnected a class is within the system. If a class ranks high in closeness centrality, it means changes to it can have a widespread impact, or it could be frequently affected by changes elsewhere. Utility classes like the design by contract utility often appear in this metric, but they aren't the problem since they rarely change. However, business logic classes that change frequently, you definitely don't want to see them here. Now here's the first key advantage of graph-based analysis over tools like NDepend or SonarQube. Graphs are an abstraction. This means you can easily modify which nodes and edges are relevant for your analysis. By changing the graph topology, you immediately get a new perspective, shifting your focus in different directions. Unlike static tools, this approach lets you tune the analysis dynamically to uncover different aspects of complexity. The second advantage is that graphs allow you to adjust the level of analysis dynamically. You can drill down into class-level dependencies for fine-grained insights. Or you can zoom out to analyze namespaces, assemblies, components, features, or even entire services. But here's the catch. Meaningful insights depend on defining clusters properly. And how the tool we use today can help you with that, I'll explain in this video.